I'm going to review some basic stuff on Archimedean fields. So let's just give a definition. A local Archimedean field will be a topological field isomorphic to the real numbers or the complex numbers. So as topological fields, the real numbers have no automorphisms and the complex numbers have a unique automorphism. So note that if I from K to L so is an inclusion, or is not an isomorphism, is a morphism of topological local fields sorry, what was the term I used? I used local Archimedean fields. Which is not an isomorphism. Then we'll have then there exists some alpha from K to the real numbers, some isomorphism. There'll exist a beta from L to the complex numbers, such that alpha inverse composed with this inclusion composed with beta is from the real numbers to C is the standard inclusion. Okay, so we have the objects that we're going to talk about now. I want to talk about, in this context, the angle magnitude decomposition. So let K be a local Archimedean field. Then what we're going to define is we're going to have OK star. This is going to be the group of units. And we can define the order in the following way. So this is just going to be K star mod OK star. And there are some interesting observations to make. So observations are, first observation, that the absolute value, the usual absolute value, we can take here, and we can take it, since these are all going to be units, this is an isomorphism. Okay, the other thing we can do is that so K star is going to decompose into OK star cross this order. Okay, and this is what I meant by the angle magnitude. So, so this is the angle, and this is the magnitude. So I'm just going to write down the standard examples. So I'm going to write one example that deals with angle magnitude decomposition. The other thing I just want to write down to remind you that there's kind of an interesting way to write down, so this is standard. Okay, so let's say greater than 0 here, since we're having a B unit. So there's kind of an interesting way to write down not the ring of integers. So okay, so let's do something here. So let's let K be the real numbers. We can do this with the complex numbers too, but for this this doesn't really make sense. Okay, so if you just take things with absolute value less than 1, this doesn't make sense. But if we take the monoid, then this does make sense. and this is a multiplicative monoid. So even with the real numbers, we can start to do something. So this is, you can kind of do some semi-interesting valuation theory. So this is, this is cool. Okay, so we don't have the ring of integers, but we do have the monoid of integers. I just wanted to mention that. Okay. I'm going to go on and I'm going to define things like angular regions and things like this. So let K be an Archimedean field. Okay, so an angular region is a subset A of the units such that 1, so B is completely contained in OK times. Okay, so B is contained in here, and it intersects each connected component in a connected component. The second thing that I want to say is that here, this dude is an interval of the form 0 to lambda. Okay, so what are the restrictions that these do? Okay, so let me just say this is a restriction on angles. This is a restriction on magnitudes. Also, this is a restriction for the real numbers in the case that you can't just have like one piece here, so you're gonna have to have both pieces. So let me write that down again. So condition 1 is something on angles, and it says that your regions need to look like this. So they need to be full. Okay, or they need to be, here's the real line, they need to be like this in the real case. Okay, and then to the condition on magnitudes, it says, okay, well, you can take a region like this. This is okay. Maybe I should show that these are removed. This is okay. Okay, but regions where I only take this piece here, this is not okay. Okay, similarly, you can't have an infinite piece here. This is also, so if I did this whole thing here, remove this, this is also not okay. Okay, so let me just give a definition. Just more terminology. If we have an angular region like this, okay, so there's a parameter. This thing will have length lambda. This is called the tip. Okay, this whole thing is A, and this region here is called the boundary of A. Okay, the end part. Let me give another definition. And this will come up in morphism of Frobenioids, and this is actually the origin of the terminology in Frobenioids. So an angular region A, which has its magnitude and angle, or angle and magnitude, is isotropic if it has all the angles. Okay, so this region here is isotropic. Okay, but if we just have like a piece like this, this is not isotropic. Okay. Another thing to say is that so let A cross C and be angular regions. Okay, we say that A and A prime are coangular if and only if they have the same angular component. Okay, so what are examples? So here we could take a region like this. We could take like a much bigger region, the same angle. So these two guys are, yes, these guys are coangular. Okay, the other thing that we could do is we could take this maybe same region here and we could compare it to another region like this. So these are not coangular. Coangular. So this is a no. Okay, so one of the things I was trying to understand was okay. So I guess we'll come back to this in a second, but this is going to have to do with coangular morphisms for Frobenioids, and I have to define the relevant Frobenioids first. So, okay. So let me make some remarks. If we take a vector space over one of these local Archimedean fields, then we can talk about angular regions in K. Okay, so we define the order here to be this minus here, these units. So this is like the projective space of V. I'm just going to remind you that this is just V with the 0 element removed. Okay, and so if we think about this, if V is R3, then ord V is R3 minus R times, and so this is like the directions. Okay, so this is the directions and not the magnitude part. Okay, so we can talk about angular regions in here, and so angular regions they'll just look like little regions here. So maybe I can make another. Okay, so this is an angular region. So they make sense in vector spaces. So we'll remove that piece here. And isotropy makes sense. So coangularity and isotropy. So this is an isotropic region. Okay, and so also coangularity makes sense too. Sense too. Okay. So I can talk about tensor products of angular regions. Okay, so we'll take vector spaces v1, v2 over some local Archimedean field. We're going to take a1 and v1 and a2 and v2. These are going to be angular regions. Maybe I can underline this. Okay. Then what we'll define a1 tensor a2. This will be the set of a1 tensor a2, where a1 is in a1 and a2 is in a2. And this will be, of course, contained in the tensor product of these two guys. So what's going on here is we could have, say, one region and another region. So let me draw them. And we can tensor them to get a new region. It should be twice as long. To get a new region. This is the idea. Under morphisms, so So we can talk about behavior under morphisms of fields. So so I'm going to kind of change it. I'm going to talk about covers now. B finite tall cover. Okay, and let's take A contained in V be an angular region. So this is going to be a vector space over K, an angular region. And what we'll define is we'll define the pullback of the pair VA. And so this is going to be defined to be some V prime and A prime. And this is going to be a vector space in an angular region where V prime is just the pullback of V, which is like this. We just base change. And A prime is going to be, well, the image of A when F is an isomorphism. And it's just going to be the isotropic orbit of A if F is not an isomorphism. Okay, so like here, when things go bad, you just kind of like make the big thing, make a big isotropic orbit. So I'm going to now define some notions of elementary or some Archimedean Frobenioids. So we're going to work with this base category. So this is just the stupid category. Category of covers of R. I say that it's stupid. So, okay, so first of all, there's going to be maps of topological fields, essentially. And I want you to know why it's stupid, because these guys, this is just two dudes in the set. Okay, so, all right. So now I'm going to define this. I'm going to give you the definition of the elementary Archimedean Frobenioid, and so this is in Geometry of Frobenioids 2. Okay, so the elementary Archimedean Frobenioid is defined to be this. I'm going to do it blackboard F infinity. This is going to be the elementary Frobenioid associated to this gamma infinity. So we just need to define a monoid. So this is going to be over these covers here, where this monoid here is this stupid monoid, gamma infinity, here, two monoids, takes K and maps it to the order of K, which is K star mod OK star here. So this is the value group here. Maybe I could call this gamma of K. Okay, so it maps it to the magnitude. Okay, so that being said, let me go and talk about the basic Archimedean Frobenioid. So I have this elementary Archimedean Frobenioid. I'm going to build one on top of it. So, so again, we fix that basic cover, and then we're going to let F infinity. I don't know if this is the best notation, but let's go with A infinity. So A infinity. So this is going to be the basic, so there's going to be one of them. Like the previous thing, there's only one of them. The basic Archimedean Frobenioid. This is going to be over again covers of R, that stupid category. And the objects of this category are going to be triples spec K, V, A. Maybe the A is not looking like such a good choice up there, but oh well. Okay, spec K is a cover of spec R. Okay, so then, and V is a K vector space, and A contained in V is an angular region. Okay, morphisms are like so. So I'm going to try and fit it onto this page. So spec K prime, V prime, A prime maps via phi to spec K, VA, where phi is 3 parts. It is, maybe I should do this, sigma, and then degree phi. I'm going to call this D, such that F phi is a morphism, is just the cover map. Okay, the sigma, so this goes from V prime to the dth power to the pullback here. And this is again V, just tensor K to K prime, and this is such that the angular region is going to be contained in the base change of the angular region here, like so. Okay, so this is the condition here. Okay, so a morphism, we just have these triples here. So we build them out of vector spaces and angular regions. And so this is the basic Archimedean Frobenioid. So we have an example. Let me just kind of like give you the idea. So we could have like K prime being C, K being C, and then what we're going to look for is for, you know, so suppose we have an angular region here, A prime. So this could be, say, like pi over D, the angle here, and it needs to map into some bigger angular region that contains it. It doesn't necessarily need to be the whole thing, but if this is degree D, right, then it'll go all the way around here. Okay. Not getting this piece here. So, A. Okay, so this is kind of the idea. Okay, so now I'm going to give some more definitions. And these pertain to definitions for general Frobenioids. These are the definitions that motivate for things. So we'll take a Frobenioid element in the basic Archimedean Frobenioid, and we'll say that it is naively isotropic if the angle of x is, you know, like the whole thing. The whole thing. Okay, that's our dude. Okay, and then we'll say that F, our morphism, in the basic Archimedean Frobenioid is naively coangular if and only if. So the angle of of y is equal to the image of the angle of x. Okay, so this is the idea. So this is what this will be the coangular part. So I guess this is an angular region. This is really just the angle part. Okay, yeah, this is just the angle part. So I don't need to. I'm not worrying about magnitudes here. So there's kind of a claim, and that maybe people can help me out with. So the claim was the idea. Let's see if I have it here. Maybe I didn't write it down. So so the question / exercise. So recall that we had a notion of isotropic and coangular for abstract Frobenioids. So I may have a video on adjectives of Frobenioid morphisms. Okay, so the show that F is, or say a Frobenioid element in F infinity is naively coangular. Oh, sorry, is naively isotropic if and only if it is isotropic. Okay, and then you can say the similar question for coangularity. All right, so that's that. Let me now tell you what a Archimedean Frobenioid is. So I guess definition. Let D be a totally epimorphic, connected category. So totally epimorphic just means every morphism is an epimorphism. I don't know why they say just totally epimorphic. I don't know so maybe someone can tell me what the difference between an epimorphic category is and a totally epimorphic category. I mean, so what an epimorphic category is normally. Because I would think that an epimorphic category would be a category where everything's epimorphisms, but apparently that's supposed to be what totally epimorphic is. So anyway, if anyone knows, please tell me. Okay, so let D be a totally epimorphic category. We're going to take a functor to this stupid category of coverings. Okay, and let A infinity be the basic Archimedean Frobenioid. Okay. So an Archimedean Frobenioid is one of the form like this. So this is the definition of an Archimedean Frobenioid. Okay, so note that here. So note that the underlying category. So maybe you take this to be a definition. Is this fiber product category, and the underlying monoid is this, let's call it f star gamma infinity. So this is the stupid one, which is just precomposing with this functor. So here's a question. So lemma / question / exercise. So fix one of these dudes. So D is going to be connected, totally epimorphic. Okay, then I think we have the following. So we could take an elementary Frobenioid. This is the same thing as pulling back this category. And so so the proof for the objects here is we take f star f of gamma infinity here. We'll take these covers. Okay, and then okay, so this is this guy here, and then we can see on objects that these are going to be the same. So f gamma infinity. So D here. So I think that we get the objects. Objects D here. And so this becomes, these two things cancel because the underlying objects of this category are just the objects of R0. And so this just becomes the objects of D. Okay, so that's one thing. And then, so the other thing that we need to check is the morphisms. Am I really checking the right thing here? I'm actually kind of worried now. I'm kind of confusing myself, I think. So maybe I'll cut this out. Maybe I won't. We'll see.